Class, it's Mr. H here, gonna finish off 6.2. This one's on linear velocity and angular velocity. So some cool examples of circular motion and the speeds of circular motion, basically. So this little animation helps to describe what we're talking about. So if you see what we have here, there are a couple of points on different circles of different sizes. And I'm just going to hit play. So if I put these points in motion, we can talk about two things. We can talk about just how fast the point is moving, right? That's just like regular velocity, like the motion of a car, just the path happens to be circular, but that would be called linear velocity. I mean, even though it's not moving in a line, but we use that term linear velocity, just that's your standard velocity, like miles per hour, that kind of thing. The other type of motion here is what's called angular velocity, and it's the change in the angle per unit time, right? So how is that angle changing as time goes on, right? So notice, like if we talk about this dot, I mean, think about that ray going to the origin and think about how that angle is changing, okay? One thing to note about the two dots on this animation, both of them have the same angular velocity, right? Because the angle is moving at the exact same rate. If you compare the two dots, they're hitting those rays at the same time, right? So the angular velocity, the rate at which the angle is changing, is the same. However, if you compare the two dots, you can see that the orange dot is going faster, right, than the, what's that, purple? So the orange dot would have a greater linear velocity than the purple dot, okay? So that's what we're talking about. We're going to put some formulas to this and do some examples. So let's jump to the handout for that. So your formula for linear speed or linear velocity, it's the same as you've probably seen before. It's the standard distance divided by time, or we could just call that S over T. That looked weird. Let's not do that. Let's go back to yellow, that one, right? That's the formula we'll use. And then that S has a little formula as well, right? So when you find S, that's arc length, which we used R times theta, where theta is in radians. So another version of this is R theta over T, which we'll probably be using more often, right? Because we'll have to find that arc length. Okay, so when you have to find linear speed, use that formula. Angular speed is the rate at which the angle is changing. So that is this one, right? And we use omega for that. So that's the Greek letter omega. So we're going to use that symbol to mean angular speed, okay? So a summary of the formulas, we have angular speed, linear speed with its variations, and then there's even one more right here, because if you notice that second one, V is equal to R theta divided by T, right there within that formula, you have a theta over T, which is right there, which is the same as omega. So that can simplify even further. And sometimes that can come in handy, can be handy. Okay, so that's all your formulas and the setup for this. Let's do some examples. Last page on this handout, page 6. Let's find the angular speed in radians per minute of the blade of a wind turbine turning at a rate of 15 revolutions per minute. So we want angular speed. So I'm going to use my angular speed formula. Okay. And then what do we know? What is the angle? Well, I know we're doing per minute, so my time is 1 minute. And I just got to figure out what was the angle that was rotated through in 1 minute, right? So there were 15 full revolutions, And each revolution is 2 pi, right? One revolution is 2 pi radians, right? So I'm going to do, for my angle, 15 of those. 15 times 2 pi. And that's in radians, right? So if I calculate this out, that's 30 pi. So my angular velocity is 30 pi radians per minute. Okay, so there's a good example of finding angular speed. How about linear speed for number 22? For the linear speed, I've got v equals, I know it's s over t, but I like to just jump right to r theta over t. That's typically what's given on these problems. The speed of a point on the edge of a 16-inch wheel. So that one's a little unclear. Are they saying, is that 16-inch a radius or a diameter? Typically, if it doesn't say radius, it's probably diameter. So let's assume this is diameter. So then the radius is going to be that divided by 2. So it's a kind of a kid's bike here. 8-inch diameter, blah, blah, blah. 8-inch radius. Okay, so my radius is 8. This happens, let's see, it's rotating 40 times per minute. So again, my time is going to be 1 minute. And then what is that angle theta? So 40, 2 pi's, right? So I'm going to put in a 40 times 2 pi, right? And that's the theta, okay? So if that helps, I can highlight this is the theta. R is the 8 and the T is a 1, okay? And then I'm just going to calculate that out. This says just type an exact answer using pi as needed. So what's this going to be? 8 times 80, 640. So this is 640 pi. And then what is this? Okay, this is inches, right? So inches per minute. And talk about the units of measurement here, comparing angular velocity and linear velocity. Notice that angular velocity is always in radians per unit time, whereas linear velocity is some distance per unit time, inches, feet, miles, meters, centimeters, okay? And I know that's inches because this was in inches, it was 8 inches, right? Okay. How about the linear speed of a point on the equator of Neptune? Whoa, Neptune. All right, and we've got to know the radius of Neptune, and it completes 1 revolution every 18 hours. Okay, so linear speed, all right, we're back to my linear speed formula, r theta over t. R is that 15,300. And then how about theta? Okay, 1 revolution, and each revolution is 2 pi radians. So that's 1 or 2 pi. So I can do 1 times 2 pi or just 2 pi. And this is happening every 18 hours. Okay. And then again, it just wants exact. That's like the homework. I think a lot of them are exact. So maybe 1 or 2 wants some rounding, but so model the homework there. All right. So now I'm going to just calculate 15,300 times 2, right? And then divide that by 18. Okay. And I'm just leaving the pi out of the calculation because that's just going to be in the answer. So I'm getting 1,700, right? And that's pi. And that's in miles per hour, right? So again, that 1,700 came from 15,300 times 2. Don't really need the 1, and then divide that by 18. Okay. Last one. Let's try this one. This one, we have a radius of 10, okay, and 210 revolutions per minute. How fast is the bicycle traveling in miles per hour? So right there, I know, because they talk about a distance per unit time, that's linear speed, right? And this one wants miles per hour. Okay, so we'll get to that, but let's just start off with our formula. V equals r theta over t. The r is 10. Let's see, 210 revolutions per minute. That's 210 2 pi's. That's the theta. I mean, notice the trend here on all these. When you're finding theta, because they're always giving you revolutions per unit time, just take the number of revolutions times 2 pi, and that's going to be theta. Okay, and then per minute. 1 minute down here. Okay, so if I calculate all that together, that looks like 4,200. That's 10 times 210 times 2 pi. And then this is in, let's see, what was that, 10? It was in inches. So this is in inches per minute, which that could be a fine answer, except it wants miles per hour. Dope. So I got to keep going here on this one. And it just wants some rounding. If it says rounding, I'm going to probably, well, not probably, I am going to do my pi approximation, use my pi key on my calculator. Okay, so let's now convert this 4,200 pi inches per minute. We've got to convert this to miles per hour. And the way to do that is dimensional analysis, they call it sometimes. You might see this in science classes a lot. We're going to multiply by conversions. So let's do the distance first. There are 12 inches per 1 foot. Right? And notice here, the reason I'm putting inches on the bottom and feet on top is because now the unit inches will cancel, and I'm left with feet. So if I stopped here, I would have feet per minute, but I don't want that. I got to keep going. So the next one, let's get rid of the feet. So there's right there, gave me a clue, 5,280 feet per 1 mile. That's good because now the feet cancel and I'm left with miles. So if I stop now, I've got miles per minute. Okay, so finally we got to get rid of the minutes because I want per hour. So one more conversion here. There are 60 minutes equal to 1 hour, right? Minutes on top, so it cancels with the minutes that was on the bottom over here. Now, when all the dust settles, I'm left with miles per hour. And then I just have to do my calculation, right? Now, when I do this calculation in my calculator, let me just show you, because there's a lot of calculations involved here, but there's a bunch of numbers on top and in the denominator. So let's see how we would put that in. I would put a parenthesis starting at the top, and then I'm going to type in the 4,200 and then times pi. And then there's one more number up there that's not 1. That's the 60. And then close the parenthesis. And now divided by, and then open a new parenthesis for the numbers that are in the denominator, 12 and the 5,280. Okay. And then hit enter, and we get about 12.5, and that would be in miles per hour. And we've got it. We can write that in and call it good. All right, so I hope that makes sense. Give those problems a try. Let me know how they go. If you have any questions, send them my way, and I'll definitely help you out. Okay, talk to you later.